In this video, we're looking at identifying functions using finite differences. As I mentioned in the previous video, I recorded all of these videos and then they would not upload, so I had to record them again, which is why our sheets are already filled out and we are just going to talk about what I did when I recorded the video that no longer exists. So it says, for the function shown, state the base of the function and calculate the finite differences. So we have 3 times 2 to the power of x plus 5 minus 7. So the first thing I did was what it asked. I stated the base. So the base is the number that is holding up my exponent, which is that 2. So this has a base of 2. Then I went and I looked at the table and I calculated the differences. So on the x side, I noticed that I was adding 1 every time. And then on the y side, I noticed that I was not adding 1 every time. So I did 41 take away 17 to get 24. I did 89 take away 41 to get 48. I did 185 take away 89 to get 96. And 377 take away 185 to get 192. So taking a look at this, if it was polynomial, then I would do the differences again and again, and hopefully I would end up with the same number as my differences at some point. But this is not polynomial, it is exponential. So with an exponential function, I only do the differences once, and then what I look for is I look to see, are we multiplying or dividing those differences by the same number every time? So I took 48 and divided it by 24, and I found that it was being multiplied by 2. 24 times 2 is 48. I took 96 and divided it by 48 and got 2. And I took 192, divided it by 96, and also got 2. So when something is exponential on the y side, you will notice that once you've done the differences once, those differences should have a common multiple. So they should either be all multiplied by the same number, or they could also be divided by the same number, but that's what we're looking for when something is exponential. Okay, we're going to take a look at logarithmic. So our logarithmic functions, it says, for the function shown below, calculate the missing value using the equation, state the base of the function, and calculate the finite differences. So I have g of x is negative log base 3 of 1/2 x plus 10 minus 1. And the number that was missing, because it mentions finding the missing value, was the y value that went with 8. So over at the side, I calculated the value by putting 8 in for x. So I did 8 plus 10 is 18, and then times 1/2, or 1 divided by 2, was 9. Now, log base 3 of 9 is asking the question, 3 to what power gives me 9? So 9 is 3 squared. So log base 3 of 9 is actually just 2. I multiplied the negative 7 and the 2 to get negative 14, and then I subtracted 1 to get negative 15. And I filled that in on my table. Now, I calculated the differences because that was the next thing. Oh, nope, I stated the base. The base here is log base 3, so I stated that the base was 3. And then it asks us to do the differences. So on the x side, I noticed the differences weren't equal. They were equal on the polynomials, they were equal on the exponentials, but they were not equal on the log. And then I also did the y side, and I found that those ones were equal. So if this was polynomial, then the numbers would have to be the same on both sides. It is unusual that it's on the x side that the numbers are different. But if I think about the relationship between exponential and logarithmic functions, they are inverses of each other. So in our graphing unit that we've been working on, when you're trying to find the table of a logarithmic function, you can take an exponential function and then just trade the x's and y's. So here, when I have an exponential, we have a common multiple that shows up on the y side. With a log, those x's and y's would have been switched, so now it's the common multiple that you're going to see on the x side instead. So I did notice that from 4 to 12 we were multiplying by 3, from 12 to 36 we multiplied by 3, and from 36 to 108 we multiplied by 3. So it's very similar to the exponential, but instead of having a common multiple on the left side or the y side, we have the common multiple on our x side instead. So just to kind of finish summarizing everything up, we're going to take a look at the little table that I filled in at the bottom here. So when something is polynomial, what you want to do is calculate the differences, right? And you want to keep going and doing the differences until the ones on the y side are all equal. So I wrote differences on the y side are all equal. That's how I know that it's going to be polynomial. And then for its relevant information, the degree of the polynomial equals the number of times that you had to do the differences. All right, for an exponential, what we do is we calculate the first differences. We only do it once. And then on the y side, we are looking for a common multiple. And if we see that, it is exponential. And then our base is going to be whatever that common multiple happens to be. Okay, for our logarithmic function, you want to do those first differences again. And then it's the x side this time that has a common multiple. And then the base of the function is the common multiple. So what I have written down here at the bottom is the sequence that I normally follow when I'm trying to identify the type of function. So the first thing you do is the first differences. Do them on the x side, do them on the y side, right? And then you want to check to see if it's exponential or logarithmic. So if it's exponential, you're going to notice that on the y side, those differences are all being multiplied by the same number or divided by the same number. If it's logarithmic, you're going to notice on the x side that all of the numbers are being multiplied or divided by the same thing. And then if it's not exponential or logarithmic, then I'm going to continue doing those first differences on the y side until I hit ones that are all the same. Or if I run out of points, then I know that we just don't have enough data to make any conclusions. Okay, so there are practice questions attached. Have a great rest of your day.